Hello and welcome to Cognito Key. My name is Serby. Have you ever stopped to think about what's actually happening inside your computer when you've got a dozen tabs open, music playing, and you're typing away in a document? Today, we're going to pull back the curtain on the secret that makes it all work: memory.
Yeah, think about it. You're browsing, you're listening to songs, maybe writing an email, all at the same time. Your computer is doing this incredible high-speed balancing act. And the real magic behind it all is in how it manages its memory. So, to make this super simple, we're going to use an analogy. Just picture your computer's main memory, its RAM, as one single, gigantic, empty bookshelf. It's just waiting to be filled up. Okay, let's get into it. Every single program you run, your web browser, your music player, that game you love, is like a book of a certain size. And the operating system, its job is to be the librarian and find a spot for each of these books on our memory bookshelf. Now, the simplest way to do this is something called Contiguous Memory Allocation. The name pretty much gives it away. Contiguous just means all in one piece. So every program or every book has to be placed in one continuous, unbroken block on our shelf. You can't just tear a book in half and put one part here and the other part over there. It doesn't work like that. Right, so even with this really simple rule, one program, one block, the operating system still has a choice to make. Does it organize the shelf beforehand into neat little sections, or does it just leave it as one big open space? And this leads to two main strategies. So you've got two ways to organize the shelf. On the one hand, there's fixed-size partitions. Think of this like pre-building equal-sized cubbies on our bookshelf. Each program gets one cubby. It's simple, sure, but also pretty limiting. On the other hand, we have variable size partitions. Here, the shelf is just one long open space, and the OS finds an empty hole that's just the right size for each new program. This is way more flexible. So let's stick with that more flexible, variable size approach. Now, our operating system really has to put on its librarian hat. You see, as you open and close programs, they leave behind all these empty gaps, or holes, of all different sizes, all over our bookshelf. And this is the million-dollar question, right? If a new program comes along and it needs, say, 10 megabytes of space, and there are 3 different empty holes on the shelf that are big enough, which one should the OS choose? This decision actually has huge consequences for how efficiently our memory gets used. So it turns out our librarian has 3 main tricks up its sleeve to solve this puzzle: first fit, best fit, and worst fit. Let's break down how each of these works. First fit is, well, exactly what it sounds like. It's the simplest and fastest approach. The librarian just starts at the beginning of the bookshelf and scans along until it finds the very first hole that's big enough. It plops the book there, and it's done. Super quick, but you might end up using a massive hole for a tiny book, which isn't exactly efficient. Next up is best fit. Now, this one is a bit more thoughtful. Here, the librarian scans all of the available holes on the entire shelf. Then it chooses the one that's the snuggest fit, so the smallest hole that is still big enough. The whole idea is to minimize waste by leaving the tiniest little leftover sliver of space. And then we have worst fit. Now, I know, it sounds like a terrible idea, but hang on, there's a clever logic to it. Just like best fit, the librarian scans all the holes. But this time, it picks the absolute largest hole available. The thinking is, by putting the book in the biggest spot, the leftover piece will also be very large, and hopefully still big enough to be useful for another program later on. So these strategies all seem pretty reasonable, don't they? But they all lead to the same fundamental problem. Over time, as we keep putting books on the shelf and taking them off, our nice, clean bookshelf starts to get messy. It gets filled with lots of small, useless gaps. And this mess has a name: fragmentation. And this mess comes in 2 flavors. First, there's external fragmentation. This is when we have enough total free space, but it's all chopped up into these tiny, unusable pieces. It's like having lots of little gaps, but none of them are big enough for a new book. Then there's internal fragmentation. This happens back in that fixed-size model where you put a small book in a big cubby and just waste all that empty space inside. So let me give you a perfect example of why this is such a headache. Imagine you check your system and it says you have 40% of your memory free. That sounds amazing, right? You'd think, great, I have plenty of space for a new app. But because of external fragmentation, that 40% is scattered all over the place in tiny little chunks. The single largest contiguous block you can actually use is only 5% of your total memory. So even with all that free space, you can't launch a new program that needs 10%. It's a huge problem. So
our bookshelf is a total mess. Is there any way to clean it up? And what does this all mean for this memory allocation method? Let's find out.
Well, yes, there is a solution to clean up that external fragmentation mess, and it's called compaction, or as our librarian would probably call it, time to tidy up the shelf.
Compaction is pretty much what it sounds like. The operating system basically pauses everything for a moment and shuffles all the programs, all our books, down to one end of the shelf. This pushes all those small, scattered gaps together, merging them into one giant, usable block of free memory. It works great, but as you can imagine, moving everything around takes time and processing power.
So let's sum it all up. The big advantage of contiguous allocation is that it's simple for the OS to manage, and it's fast. Once a program is running, all of its data is in one place, so accessing it is super quick. But the disadvantages are pretty significant. It wastes a lot of memory through fragmentation, and it's really inflexible. A program can't easily grow larger than the space it was first given.
Which leads us to a final, really fascinating question. Given how wasteful it can be, why was this method so important in early operating systems? And more importantly, what clever, non-contiguous solutions did engineers come up with to overcome all these problems? Well, that is a story for another time.
If this explainer helped you understand your computer just a little bit better, please subscribe to Cognito Key. And don't forget to like and share. Thank you so much for watching.